I hope it's recording. I didn't get a beep beep. Usually gives me a little countdown beep. By now it's probably recording. And here I am wasting time. So uh, we need to talk about this final page of the 4-page packet. So as you can see here, this is what your graph should probably look like. Yeah, I had to kind of extend, the position axis down below the zero. So it would actually have a negative area, which obviously you were able to do easily on your sheet because I better get myself over here because you could make your grid whatever size you wanted to. Of course, I went by threes on my interval for the position axis in meters. And I went by twos on the time axis because I only had 6 boxes and I needed to get out to 7 seconds. So, going by ones wasn't going to work. So this is what my graph looks like. Now notice, I drew a best fit here. I didn't just go and take a left turn here at the -3. I carried it all the way until it hit the y-axis. And apparently it's hitting the y-axis at about -6. So where did the object start? Well, it looks like the y-intercept is -6. Oh, come on. Oh, geez. Always, always. At -6 meters. -6 meters. Boom. Hopefully that's what you found. And it says it says how fast is the object going and in what direction? Well, that means we need to find a slope. So I suppose I could just use, because we definitely have the line crossing like perfectly at grid intersections. And we have data points that are perfect at grid intersections because they're actual data points that are perfect, which is unusual. And so I'll just do this and take that all the way down to the 0 and then over here to this area. And oh, look at that. That's perfect. So that gives me a rise of what? Well, looks like 18 meters. 3, 6, 12, 18. Yeah, that's 18 up there. So it gives me a rise of 18 meters. And that's a run from 2 to 8 seconds is a run of 6 seconds. And so hopefully you remember that velocity is change in position over change in time. And so that is 18 meters, positive 18 meters, in fact, of position change. And that's a 6-second time interval. And so my velocity is positive 3 meters per second. Now, oops, might help if I put a number in there. Positive 3 meters per second. Now, here's the deal. If you're answering this question and you say that the answer is just 3 meters per second, well, then you only answered the first part. You answered how fast. Direction also needs to be part of your answer. Now, I took care of both at the same time because I said it was positive 3 meters per second. So you could just say 3 meters per second, and then in answering the second part of the question, just say positive direction, or just say positive 3 meters per second, which has direction wrapped up in it. You can't just leave the positive off. Well, yeah, but isn't it positive if you don't put a positive sign on it? Yeah, technically according to math. However, I'm not going to assume that you knew that the direction was a separate part than just the number. So I don't know it's positive direction unless you put a positive sign on it. Let's put it that way. Okay, so you have to communicate to me that it is a positive direction. And moving on. After 10 seconds of travel, where would the object be? Well, now here's the deal. On your graph, you might be able to see this. On my graph, I can't because my grid's not big enough. So since my time goes out to 10 here, I do have 10 seconds, but I don't have anything past 18 meters here on my graph. So I'm going to use the equation. You might have been able to read it off your graph. I couldn't, so I have to use the equation, which means I need to write the equation of the line here in my little blank here. So I would say that position equals 3 meters per second, probably should keep it positive, times time plus -6 meters. Again, negative 6 meters because we know that's the y-intercept, and so that goes in for my b. That's my equation. But they want to know after 10 seconds. So after the 10th second, where is the object? That means I put 10 seconds in for time. 10 seconds. That's not 105, that's 10 seconds. And so that seconds cancels that seconds, and I get positive 3 meters times 10. Positive 3 meters times 10 is positive 30 meters. Plus negative 6 meters, I can't forget about my y-intercept out there, which means that my position is positive 24 meters would be the position. Now, that's not how far the object went. Okay? Remember, positive 30 meters, that's how far the object went. It started down here at negative 6 meters and went all the way past the 18 up to 21 and then 24, which would be up somewhere in this region here. So the change in position was 30 meters, positive 30 meters. But since the object started 6 meters behind the zero, the person's not getting to the 30 meter mark, only getting to the 24 meter mark. Hope that makes sense. So like we had talked about before, this is your change in position. That's your delta x. This is your initial position, your xi, your initial position. This is your final position, your xf. Okay? I hope you're getting that. And these graphs here. So for these, you need to, I would say, divide them out into sections. Okay? So section 1, section 2, and then finally section 3. And again, I would do the same thing over here. Section 1, section 2 is a little narrower, and then section 3, it's even narrower. So 1, 2, 3. Now, what color? I mean, what? Oh, hold on. Let me write this down. Here's the thing. What is it about the position time graph? What do we have to look at to know what's going on with the velocity graph? What do we have to look at here? What is it about these lines that we have to know? I hope you're thinking the word slope right now. We have to know the slope of the line. So if you, let's see, describing, oh my gosh, I can't even write. Oh my gosh. Describing the slope. So describing the slope here on a position time graph means you are describing what? The velocity. The words that you use to describe the slope are the same words that describe velocity. Now, do not say going down. It's going down. It's steadily going down. That does not describe the slope. That's describing the line itself and where the line's going. I'm not trying to describe that. I need to describe the actual slope. What kind of slope is this? Negative, right? Negative slope, and what? It's constant. It's not curved. It's a steady, constant, but negative slope. Describing the slope describes the velocity. So that means over here, we have to sketch a steady or constant negative velocity. How do you do that here? Well, That's zero velocity. These are positive up above, and these are negative down below. So our line's going to have to be where? Below the zero, and it's going to have to be steady, not getting bigger, not getting smaller. So I would say a line like this. That is a negative velocity. It's below the zero. Remember, this is zero. These are positive velocities. These are negative velocities. So if you describe the slope of this line right here as negative slope constant, then you need to show a negative velocity that's below the zero and constant, not going up, not going down. I hope that makes sense. The center section, how would you describe that slope? Hopefully you're describing it as zero. That is zero slope, no slope. Describing the slope describes the velocity. So if you have no slope, you have no what? No velocity. Where's no velocity on that graph? On the t-axis. Zero velocity, none. This section, section 3, describe that slope. Positive, right? Positive and constant. And in fact, how does the steepness here compare to the steepness here? Way steeper, which means it's a steeper constant positive slope, which means it's a faster constant positive velocity during this section. So where do I put my line here? Well, because it's positive, it's got to go above, right? It's got to go above the zero because it's positive. Notice how short this section is, because look how short that section is. I'll talk about that in a second. So I hope you see that it has to go up here somewhere. Now the question is that far enough up? I would say no, because that is about the same distance up from zero as this one is down from zero. So that's telling me that if this is like a -2, that this is like a negative or a +2. But we just said this line is way steeper than this one. So I would say that has to move up quite a bit. Further from the t-axis or the zero. That's a larger value. This would be a smaller value. This is closer to zero. This one is further from zero. I hope that makes sense. Now, something else to notice. That's how much time the first section had. This is how much time the second section had. That's why I made the middle section over here a little narrower, because it's less time than this one. This one is less time than this one. And then the final section, that's even less time. That's a very narrow section of the graph, so that's even less time. So this should be even smaller in terms of width. So that's one of the things you kind of have to pay attention to as you're going from the position time graphs to the velocity time graphs, is not just what each of the sections is doing, but how much time or how little time is happening during those sections. Hope that makes sense. And next one. Oh, yeah, we're supposed to sketch motion maps. We'll come back and do that at the end. Position time graph here. Again, we have sections. Let me divide it out into sections. And that one would be kind of wide like this, and then narrow, and about the same narrow. Okay, so how do you describe the slope in the first part? That's what? Positive and constant. Positive and constant is up here. How about this section? That looks like negative and constant. Maybe a little bit slower than the other ones, hard to tell. Negative and constant. What's this? How much slope is that? 0 on the t-axis. Hope that makes sense. And the last section, So I got, let's see, this wide of a section and then a kind of narrower section and then about the same width. So if that is my, what kind of slope is that? That is a positive constant slope. And what kind of slope is this? A zero slope. What kind of slope is this? That is a very steep negative slope. That means fast, faster than the first part, and negative. That means it's not just down here, it's way down here. Why? Because it needs to be further down away from the zero on the negative side than what this one was above the zero on the positive side. Let's just say, for instance, if that's like a positive 4, this seems like probably twice as steep as that. So maybe this would have to be down here at a negative 8. So maybe even further down like that. Negative 8. 8 meters per second is way faster than 4 meters per second. Just because it's negative, it just means it's in a negative direction. It's not smaller because it's negative. It's just negative direction. So less time than this one, that's narrower. So I have a narrower band here, but it's further from the zero on the negative side than this one is from the zero on the positive side. Again, I hope that makes sense. Now I got to erase this stuff here, and then we got to draw motion maps. So going back up to the top one, motion map. Let me get some of this stuff out of the way too. Oh my gosh. Okay, here we go. Motion map for, where's the first dot? That's a positive position. Yeah, that's a positive position out here. Moving in what direction? Negative direction. So my arrows are negative. And it gets about as far into the negative as what it started in the positive. There we go. Then what happens here? Not moving at all. It stops. In the negative position down here, it stops. Then what? Then it goes positive direction, but fast. And it ends up close to where it started. In terms of where it started here, it's pretty close to where it started, but it's in the positive direction going really fast. Well, the only way that's going to happen is that, oh, that's probably too long. Those are probably too long arrows. Oh, no. I probably shouldn't have made that quite so long. Oh, geez. I'm making a mess now. Maybe like that. I hope that makes sense. Again, negative direction, kind of slow, stops, and then positive direction, really fast. That's how I see it. And this one. Where is it at the beginning? Negative position. That's over here. Negative side of zero. What direction is it traveling? Positive direction. It goes past the zero all the way onto the positive side of zero. Maybe a little further on the positive side than what it started on the negative. Then travels in the negative direction. So it goes back toward the zero. Does it get there? No. Then what? It stops. Stops for a few seconds. Short of the zero. Short and never gets back to the zero position. It stops short. And lastly, oh, darn it. And all right, so this one, where does the object start? At the zero position, on the zero line. And what's it doing at first? I would call that a positive constant velocity. Yeah, positive constant velocity. There we go. And what happens during this section? It stops for a couple seconds. And then what happens during this section? It travels in a negative direction really fast, negative direction, and goes all the way past the zero down into a negative position. So it goes fast into a negative position. Hopefully, those make sense to you, looking at each section separately. So that was this. Now, next, here's what's going to be posted on your, let's see. So this right here, this is what I'm calling a quantitative review. Quantitative, because it has what? Numbers. There are quantities on the graph, numbers. So your answers are going to be numbers, values, most of them. Okay? So you are going to have to actually read the graph, figure out displacements. Hopefully you remember what the difference is between displacement and distance, because see further down here, number 10, it does ask how much distance was traveled. Here it asks how much displacement there is. Those aren't the same. Remember, displacement and distance are not the same thing. We had conversations about that. You wrote some things down about that. So you should, you will need to be able to answer these kinds of questions for the test, which is going to be the next class. So I had the students work on this in class. And then we just started to talk about some of the first 3 or 4 answers before they left. We will finish talking about those on the next class right before you all take the test. So you need to know how to interpret and read these kinds of graphs. And that's what these questions are trying to get you to do. So that's the quantitative, because there's numbers. Here is the qualitative section where there's no numbers. Now, there's 4 separate column or rows here. I would say just try to do the top row. So the top row here, what they've done is they've given you a position time graph, You need to construct, what does the VT graph look like what we were just doing on page 4 of the last worksheet. So what does translate this into what a VT graph would look like? And then write a little description of what this object is doing, like where it's starting, what direction is it going, is the velocity constant, those kinds of things. Then sketch a motion map for that motion. So I would say the top row, get the top row done. If you want to do some others, because see each line here, so this one they give you the VT graph and then you have to fill in the other 3. This one they give you the written description and you have to fill in the other 3. And this one they start you with a motion map and then you have to fill in the other 3. So I would say, at least for practice sake, do the top row, start with the XT graph, and then write down each of the other sections or parts. Put that at the bottom maybe of the quantitative review stuff from this worksheet, and then turn all that in. You can upload your picture of that for the next class. So hopefully you don't have any questions. If you do have questions, just shoot me an email and I can, or stop by if you're actually in the building, and we will go from there. So that's what you have to do for the next time, which then will be the test, to make sure you know about velocity for the test. I think that's it. I think I'm done sharing. So take care of yourselves until I see you next time.